Hello again. I hope you had a pleasant lunch and break. So just remind you that we should leave here by 5:30 maximum to the hotel to get the bus, and the other people will have cars and Uber, etc., to go to Park Tech. I think Laurie has sent the location and some instructions how to find it. Or if you get lost, just ask for the Volkswagen car plant. It's just, adjacent to the Volkswagen car plant. Everybody knows where the Volkswagen car plant is. It's a huge plant. It's a great honor and pleasure to open, the lectures by Professor Helmut Eckert, which, who unfortunately had an accident just before coming here. But he insists that he wants to give his lecture standing there. Okay, we have to respect Professor Eckert. I'm not going to describe his CV today because it's really, really, really long, believe me. And he is certainly one of the most well-known and acknowledged experts on glass structure, using different techniques, especially NMR and EPR. But he has 500 papers or something like that, published. So Helmut, thank you so much for coming, and we look forward to your lecture.
Yeah, thanks very much, dear Edgar, for the kind introduction, and for allowing me to participate in this school. I normally give talks about NMR spectroscopy in glasses because that's what I have worked on for most of the time. But Marcos de Oliveira, who follows up, will do this at around 4 o'clock. And so I thought today I'd talk about EPR, electron paramagnetic resonance of glasses. And since the technique may not be so familiar to many of you, first we'll illustrate a little bit the fundamental principles, the spin concept, the interactions of the spins with the magnetic field, the so-called Zeeman interaction, and the things that influence the spectrum that we're going to be observing and what can we learn from it. In EPR spectroscopies, there are two types of techniques. The traditional one being continuous wave EPR. We talk a little bit about experimental aspects, the simulations, and given a little bit of a review of EPR of transition metal ions, which of course are important ingredients in glasses. And then I will talk about advanced techniques using pulsed EPR, a technique that's been practiced here in San Carlos for many years by Professor Claudio Magon, and talk about these techniques, give an overview of echo-detected field sweep, EDFS, electron spin echo envelope modulation, ESEEM, and then even briefly mention some of the more advanced methods. And then, of course, all the way in, to give examples, I will show applications to glasses so that we can find out what we can learn about these. So, EPR spectroscopy, a technique, pretty much the small brother of NMR spectroscopy, also pretty much invented around the same time in Russia. EPR spectroscopy is spectroscopy of unpaired electrons. That means open shell species, which could be of different types of nature. So diamagnetic materials are not of interest here, but only materials that either have unpaired electrons as part of their structure, for instance, stable organic radicals, so-called nitroxides, then defects in solids, which are relevant, for instance, are being formed, for instance, by exposure to radioactive materials, to ionizing radiation. Then a big group of paramagnetic transition metal ions in certain oxidation states. The most important ones are listed here. And the rare earths, of course, the rare earths being a very important ingredients of glass structures for optical applications, for laser design, for optical sensing, and altering the structure of glasses as well. Boundary conditions are a little bit different from NMR spectroscopy. In NMR spectroscopy, we are usually, the species that we investigate is a major part of the sample. So typically above the level of 1 and 2%. In EPR spectroscopy, if the paramagnetic species are getting too concentrated, above this level of 1 and 2%, we have problems because the magnetic moments that are associated with the unpaired electrons, they interact and result in dipolar broadenings that destroy the resolution. And at a certain point, we will actually not even be able to observe the signals because of very rapid spin flips that are promulgated by these dipolar interactions. So we are looking generally at magnetically diluted species at a level of 0.1 to 1 more percent or even lower. Other things that we have to bear in mind is there's not a guarantee you're going to be observing a signal because it also depends on the electron spin lattice relaxation time. And many species, for instance the rare earths, are unobservable at room temperature, except for a few exceptions like europium-2+ and gadolinium-3+. But many other rare earths, to be able to observe them, you need to go to very low temperature to slow down spin lattice relaxation. So when you're studying these species, it will be important to have a cryostat that you can cool down to liquid helium temperature. The detection limit is much better than with NMR spectroscopy because the magnetic moments are much higher, so the population difference between the Zeeman states is bigger, and the limit is about 10 to the 12 spins. And then, of course, this is the part that is interesting. The resolution depends a lot on the sample. It depends on various interaction mechanisms that are, on the other hand, important sources of information. G and isotropy, I will talk about that, dipolar broadening, spin exchange, and relaxation. So let's talk about electron spin to begin with. When all of you, not all of you, have had Physics 1 in graduation, and so let's. Electron spin was initially a concept introduced as a postulate by Goudsmit and Uhlenbeck, who tried to find an explanation why there was a discrepancy between the experimental emission spectrum of hydrogen, showing that the degeneracy of the hydrogen electronic levels is 2n², n being the principal quantum number. But Schrödinger's theory only predicted a degeneracy of n². So Goudsmit and Uhlenbeck said, okay, we can fix the theory if we assume that the electron has one additional angular momentum with a quantum number of 1/2. That means two distinct Zeeman states, +1/2 and -1/2. And that would double the degeneracy. And so that was their postulate. And then let's see how this was verified experimentally. So of course, postulate, agrees now with the theory, but it would be nice to actually have some more proof that this concept is real. So that, in order to prove that, we know from classical physics that electron spins, which means basically a charged particle in motion, will create a magnetic moment. Okay? So the classical model would be a charge here of value k, q, going on a circular trajectory, having an angular velocity v, and the radius of the circle would be r. Then basically this would create a magnetic moment. The magnetic moment is calculated as the product of the current that represents the motion, the circular motion of this charge, times the area. Well, the area is pi r squared, and the current is the charge over time. So the charge over time, that would be, you can see here, the angular be related to velocity. It's 2 pi r, the circumference over the time. So time is 2 pi r over v. So the current would be charge over time, so it would be qv over 2 pi r. So then the magnetic moment over here is given by qvr over 2. Now, angular momentum is momentum as the cross product of momentum and r. So it's mv. Momentum is m times v, angular velocity, tangential velocity. Okay, v. So m times v multiplied by r. It's 90 degrees. So angular momentum L is mvr. So then the magnetic moment, if we substitute now Vr by L over m, we find here the relationship between the angular momentum associated with this motion here and the magnetic moment. So mu equals L E over 2me. This is the classical prediction if E is the electronic charge. So that's a classical model, but an electron is not a classical particle, and in this case we would have to replace the this equation by this equation. Now S is the electron spin angular momentum, and G is now a factor with which we have to multiply this E over 2m. Yeah? So under quantum mechanical, for a quantum mechanical particle, this is the result. It's actually an experimental result from the so-called Stern-Gerlach experiment, which I will tell you about soon. G turns out to be a value very close to 2.0, the so-called Landé factor. So then we can write the magnetic moment, which is this, and we comprise these various numbers here as because angular momentum is proportional to h bar. So this now is S is now the dimensionless vector operator, and E h bar over 2me is called the Bohr magneton. So we can get mu, the magnetic moment operator, is equal to the factor G times this Bohr magneton here times the angular momentum operator associated with the electron spin. And this mu b, Bohr magneton, has this particular value. Okay. Yeah. Okay. So, we're back to the question of electron spin and magnetic moment. We saw the relationship between them, and now to detect them we need a magnetic field. So here we have the magnetic moment, here the magnetic field, the Zeeman energy, it's called the Zeeman interaction. This interaction here is the scalar product of mu times b with a negative sign. So then both of these, this is the scalar product. So it's the absolute value of the magnetic moment times the absolute value of the magnetic field times the cosine of the angle between the magnetic moment and the magnetic field. So now we need to consider that spin, angular momentum, is a quantum mechanical observable that is subject to quantization. We have a condition of quantization of the magnitude, which is s squared is equal to s times s plus 1 h bar squared. So s here is simply the spin quantum number, it's a scalar. And then there's the orientational quantization, which is the z component in one specified direction. In our situation is always the direction of the magnetic field is m times h bar, and m is the orientational quantum number. The orientational quantum number is anything between plus s and minus s in steps of 1. So for an s equals 1/2 particle, we have two orientational quantum numbers of plus 1/2 and minus 1/2. So this is the situation of the electron spin in the magnetic field predicted by quantum mechanics. The angular momentum operator is actually not directly parallel to the magnetic field, but inclined at an angle of 54.7 degrees. Okay. So how can we now detect the physical reality of electron spin? And this was done by the famous Stern-Gerlach experiment. The Stern-Gerlach experiment, we consider that if this is the expression for energy, the two states, parallel and antiparallel, depending on whether the m is plus 1/2 or minus 1/2, have different energies. So energy of this is different for plus 1/2 and for minus 1/2. And so we can take the first derivative of this expression, then we get a force. So it's basically now the minus the first derivative of dE over dZ would be equal to mu times, here is the first derivative with regard to distance. This is the magnetic field gradient multiplied by this cosine of this angle. So basically the prediction is, in an inhomogeneous magnetic field, the so-called magnetic field gradient, the different spin orientations that we see here, would, which have these two different angles, 54.7 degrees and 135.7 degrees, they will have different forces acting in different directions. Because the cosine of 54.7 degrees is positive, the cosine of this angle here, 135 degrees, is negative. So what we predict, what the Stern-Gerlach experiment predicted was Stern-Gerlach predicted is the following: in an inhomogeneous magnetic field, in a magnetic field gradient, a particle having an electron spin traveling through this inhomogeneous magnetic field exists only in two states, and these particles, depending on whether in a state of plus 1/2 or minus 1/2, would suffer forces in opposite directions. So you could spatially separate the two spin orientations. So it's a state selection, quantum mechanical state selection by this magnetic field gradient. So to prove this experimentally, Stern and Gerlach used a stream of silver atoms. So basically you create a stream of silver atoms by heating a silver wire and applying a vacuum with a little bit of a pressure gradient. So you have basically a linear trajectory of the silver atoms streaming here through the magnetic field and the magnetic field gradient, splitting up the two beams, the two orientational states. And so if the theory is correct, we would only observe those spots. If there was no orientational quantization, then one would have predicted what is shown over here, the classical prediction, because then any angle between the magnetic moment and the magnetic field could be possible, and we would get basically a broad distribution of orientations, broad distribution of forces that would range from here to here. But that's not what was seen. What was seen was exactly this, which means this experiment was extremely fundamental because it first proved that the electron spin has a value, a spin quantum number of 1/2, so only 2 orientational states. Yeah? It proved also that there is orientational quantization, that this concept is actually a real one, not just a theoretical concept. And what the experiment also was able to prove is the experimental value of the magnetic moment associated with the electron. So this is where we actually know how we actually know the G-Landé factor of 2. So of course it was important to select very carefully the material that they're using for this. And the silver atom was chosen because it has one unpaired electron in a 5s orbital. Yeah? So it has a closed shell of krypton. All the d orbitals are occupied, no spin associated with this. But this one unpaired electron is in an s orbital. So orbital angular momentum is 0. So any magnetism associated with the silver atom has to be due to the electron spin. Yeah? So, well, of course, this was highly appreciated by the community, and Otto Stern received the Nobel Prize on this in 1943. Walter Gerlach, who actually did the experiment, was at the University of Frankfurt, but the Germans weren't so popular in the 40s, and so he did not receive it, but Otto Stern was did what we now call in conceptualization. And then basically now I'm going to talk about the EPR spectroscopy. Here's some literature. All these notes will be available freely, so I will don't have to go through this. So let's now talk a little bit more about the spectroscopy. So now that we know that the spin concept is real and that we have a magnetic moment associated with it, here you see again now the so-called Zeeman-Hamiltonian, which relates the energy to the spin angular momentum. And basically the Zeeman-Hamiltonian is G times the Bohr magneton times the value of the magnetic field times the angular momentum SC. Okay. And G in the formulation of EPR spectroscopy is always defined now in terms of a pure spin quantity. If there's only spin and no contribution of orbital angular momentum, then G will be 2.0023. Yeah? But as it turns out, in real samples, we always have, in addition, we may have orbital angular momentum. For instance, for transition metals and for rare earths, that is common. In that case, the G is calculated from this formula over here, in which you have here the spin quantum number, here the orbital quantum number, here J is the sum of the spin and orbital angular momentum, the vectorial sum that you need to compute for the ground state of the electron, following the Gliebsch-Gordon rules, and divided by 2J times J plus 1. So, yeah. Okay. So, NMR, in NMR, the whole, up to now, the whole presentation of EPR and NMR is exactly the same, only difference being that for NMR spectroscopy, the size of the magnetic moment, that is the G factor, is a lot smaller, so magnetic moments are smaller, and you have frequently also other spin quantum numbers. For an electron, it's always 1/2, but for nuclei, it can be anything between 1/2 and 9/2. For all the stable nuclei, we have a distribution. It depends on the isotope. It's an isotope-specific quantity. What's also different between the two techniques is the method of measuring the spectrum. In NMR spectroscopy, under standard condition, we normally operate at a fixed magnetic field. So this one is not being changed, and we have here for spin 1/2 situation 2 levels, and here this is the energy level difference between the 2 levels that we're exploiting for spectroscopy in NMR. In EPR, normally one operates, at least in the traditional methods, one operates at a fixed frequency. Yeah? So it's here the frequency is in the gigahertz region, typically so microwaves. 9.5 gigahertz is the 9.5 gigahertz is the principal frequency and which one operates here in São Carlos, but there are other microwave sources that supply higher frequencies. And the magnetic field is being varied from 0 to a maximum value. It's a so-called field sweep method. So we have continuous wave irradiation, and the field is changed. So with the field changing, the energy level splitting will change, and that's shown over here. And basically the energy separation between the levels increases linearly with the magnetic field, and the size of the arrow, it's an energy scale here, the size of the arrow corresponds to the frequency of the microwaves. So pulsed NMR, fixed field, continuous wave EPR, swept field. And the experimental setup is shown over here in a simplified picture. We have a microwave source, typically a semiconducting device, that reaches the detector, and the current of the detector is continuously monitored. There's also then here this connection to the sample. The sample sits in a cavity. This cavity has specially engineered dimensions to create a standing wave of the microwaves and maximize the magnetic field component of the microwaves at the locus of the sample. So the sample sits in here in this cavity at a position where you have the maximum B1, so the maximum magnetic field component amplitude of the microwave oscillating on microwave. And the whole thing sits in a static magnet for the spectroscopy carried out at 9.5 gigahertz. This will be 0.34 Tesla. So it's typically an electromagnet. And then basically this magnet now is continuously swept. So it's basically now linear, the field is linearly increased by increasing the current in these electromagnetic coils. Yeah? And then basically record the detector signal. The detector signal will remain constant as long as the sample does not absorb any radio waves from the electromagnetic wave here. But then when the field reaches the condition of resonance, yeah, then the sample absorbs and you get an imbalance here in the detector. And that's being recorded as the EPR signal. Yeah? And then when the field is higher, we get off resonance again, and then we get a constant level. Now, for technical reason, it is most practical to actually record of the Zeeman energy to be proportional to G times the field strength times the spin quantum number. But it's actually a little bit more complicated. This G, which I mentioned various times already, the Landé factor, is a scalar and has a value of 2.0023 only for liquids when there's isotropic motion in a sample. In a solid state, this G is actually an anisotropic quantity, like a refractive index or like a polarizability for the Raman people. It's a quantity that depends on direction in the molecule or in the crystal. Yeah? And this leads then to the fact that the line shape is broadened. anisotropically. It's an inhomogeneous type of broadening. So basically the spectrum that you're recording in a powder will be a superposition of a number of subspectra depending on how particular the B0 field in the powder is now oriented in one particular crystallite of the powder is oriented relative to the magnetic field. This is Z is the magnetic field direction, and here for one particular crystallite we have this particular angle and we get one particular resonance line. If in another crystallite in a powder the orientation is different, we get a different spectrum. We get the maximum signal if actually the angle is 90 degrees, which is shown over here. In this case, the statistics of an orthogonal orientation are favored, so this has the highest probability. And the parallel orientation has the minimum probability. To illustrate this, I can show it with my fingers. This is the magnetic field direction. This is the orientation of the crystal. So there's one particular chance to have both of them aligned. But for the orthogonal, we have all these. We have it around the whole circle. So that's why in a powder, the orthogonal, the 90-degree orientation is much higher. So if the crystal is oriented like this, then we measure G perpendicular. If the crystal is oriented parallel, we measure G parallel. So these are two observables that we will get from analyzing solid-state EPR spectra, and that need to be related to structure. Okay. Yeah, here I'm showing the same thing, just for you to relax a little bit. We see here again for the field perpendicular to the direction of the crystal, we have one splitting. For the field being parallel to the direction of the crystal, we have another resonance condition. But this one, parallel, is much less probable, so we get a signal here. For this one, it's much higher probability, we get a signal here. And in the first derivative, we observe spectra like this. You can see here a maximum at this point, a 0 right at this point, and a minimum at the point of the highest slope, at the inclination point. Okay, this is the case for only the simplest local geometries, the so-called axial symmetry, in which we have basically an ellipsoidal G-tensor, which means that there's one preferred direction, and orthogonal to that direction it's all the same, like like what it is in an ellipsoid, in an American soccer ball, football. And this sort of axial symmetry is, however, quite common. It always exists when you have a rotational axis that is threefold, fourfold, or higherfold, sixfold, or infinite. So for symmetries such as C3V, D3H, C4V, D infinite H, we have always a signal like this. So when we observe something like this is already information about our sample. In a more general case, the line shape is predicted to look like this. We then have G values in three different directions of the crystal, and we call it GX, GY, GZ. Just to now, in this case, this would be the situation for like a C2 or C2V symmetry, where we are lacking this higher fold rotational axis. So we either observe a situation like this or a situation like this, or in special cases where we have cubic symmetry, we see no anisotropy at all, because in the cubic site, the direction of the G would have the same value in all directions. So this is one source of information, G anisotropy. Another source of information is the magnetic hyperfine interaction, which actually, so just to back up one more time to finish this up. So basically, G needs to be considered a tensor, a tensorial quantity. So a second rank tensor, of course, has 9 components, but it's normally sufficient to deal with 3 components because every tensor can be diagonalized to a form in which we just simply only have the 3 central values. These are called the principal values. So it's like with a vector. No? A vector has 3 components, but if you choose a coordinate system such that one axis lies along the vector, then we have only 1 component. So now talking about the magnetic hyperfine interaction, this is again an observable that we discuss and interpret in EPR spectroscopy. It's basically the Hamiltonian is very simple. It's the scalar product of the electron spin angular momentum operator and the nuclear spin angular momentum operator IZ. So here we're looking at an interaction between the unpaired electron and nuclei that have their own angular momenta, their own spin values in the vicinity. Yeah? So this interaction only exists, of course, at short distances. So the total Hamiltonian then needs to be considered by this, the Zeeman interaction over here and the hyperfine interaction over here. So we can consider a very simple model of a system containing of 1 electron spin 1/2 and 1 nuclear spin of 1/2, a 2-spin system. And then basically due to the mathematics of this, we find that there will be 4 energy levels, yeah, because there's 4 permutations of electron spin quantum number and nuclear spin quantum number. So for the electron spin, it's the -1/2 orientation that is lower in energy, yeah, and the one in which the nuclear spin and the electron spin have opposite orientation quantum numbers of opposite sign is the lowest state, and the one in which they have the same sign is a little bit higher in energy. So this is the electronic magnetic ground state with the the energy difference between the 2 nuclear spin states, nuclear Zeeman orientational Zeeman states. And then the upper state for the electron would be the ms equals +1/2. And again, the nuclear spin with a quantum number opposite has the lower energy, that state, and the state in which both of them have the same quantum number of +1/2 is the higher energy. Okay. So now we remember when we do EPR spectroscopy, we apply energy of constant energy of the microwaves. So the size of this arrow here, yeah, is giving us the microwave energy. Yeah? So when the size of this arrow matches a Zeeman level energy difference, then we get resonance. So you can see, so at this particular value of the magnetic field, we observe this transition, and at this particular value of the magnetic field, same size of the arrow, we see the other transition. So the resonance will be split into 2 peaks. Yeah? And the values of these energies are given over here. A is the coupling constant and will basically depend on the spin density that that the electron has at the nuclear site. So the value of A, of course, is basically then related to the strength of this interaction. So if the electron spin has S character, yeah, like in an s orbital or in an sp3 hybridized orbital, then the interaction will be strong. Yeah? Whereas p and d electron have a weaker dipolar coupling. Thank you. Yeah. Okay. So important is to remember, because it will come up later, there are selection rules. Yeah. So the selection rule for EPIs, the orientational quantum number MS, is to change by 1 unit, plus minus 1. We're looking at induced absorption and induced emission. So we get transitions from this state to that state, and from that state to this state. And the signal intensity will depend on the population difference. But the orientational quantum number of the nuclei is not changing, yeah? Because we're not doing irradiation with radio waves. We don't do NMR. Yeah? So this is only transitions that conserve the orientational quantum number of the nuclei can be observed. So that's why we are only observing here. This one from the nuclear state of -1/2 to the nuclear state of -1/2 with the electron spin state changing. And over here, the nuclear spin orientational state is +1/2, and we're going to here again to the same, conserving the same nuclear orientation state. So we only see these two, but later on I'll show you that we'll also have forbidden transition. Okay, so this is the simplest situation in which one electron spin interacts with one nuclear spin. Now, if one electron spin interacts with two nuclear spins, one can calculate the number of peaks one gets by this simple formula. It's basically the product of 2 times the number of nuclei the electron spin interacts with times the spin quantum number of the nucleus plus 1. Yeah, when we have Ni spins with quantum number I, big I. So for instance, a common situation is like this interaction with an N14 nucleus. N14 has a nuclear spin quantum number of 1. So in this case, we would actually have observed 3 lines. Yeah? 2 times N. N is a 1, then 2 times 1 times 1 plus 1. So 3. 3 peaks for interacting with one 14N nucleus. Yeah, if we have an interaction with a spin 3/2 nucleus, for instance copper, I will show some results later, then we get 4 peaks. Okay. Now, to complicate matters a little bit more, in a solid state, the nuclear hyperfine interaction is also anisotropic. Yeah? So it also needs to be described by the principal component, the 3 principal components of a tensor. Yeah? And then the 2 tensors are not necessarily coincident. So what, you also, to completely describe the system, you need to specify the angles that relate the 2 tensors with respect to each other. You can see here the green tensor is the one for the hyperfine interaction, and the yellow circles denote, let's see, the green is here, these 3. The yellow denote the G tensor. So there you see these 3 angles, alpha, beta, and gamma, relating the 2 tensors. So if you want to fully explain the EPR spectrum in terms of these analysis, you need to fit to 10 parameters. One spectrum to 10 parameters. That's a pretty hard thing. Basically, the 9 parameters are given here, and there's a line broadening parameter. So, but here, this program EasySpin, which is freeware, you can download from the internet, does what it does this kind of job. But yeah, it's still a lot of work. It would be much better if we had some more information besides this. Yeah? So one spectrum, 10 parameters, is very difficult. If the tensors are coincident, then it's easier. Then we have only 6 parameters. Then you can have a better chance to get a good fit. Otherwise, you need to include some additional strategies. Yeah? So one thing would be to change the magnetic field strength. Yeah. So here the X band, which is the 9.5 gigahertz that we're using here in São Carlos, is the most common spectrometer. And the Q band is also available. I think somewhere in Brazil there's a Q band EPR spectrometer that applies a higher magnetic field and therefore a higher microwave frequency. And there's others, W band with 3.5 Tesla, 95 gigahertz. So we can see here by the simulations, this is what the spectrum of this nitroxide radical looks like. This is an unpaired electron interacting with one N14 nucleus. You get these 3 peaks there, but it's anisotropic, and you need to somehow extract these 6 parameters, assuming that in this case actually we have coincident tensors. But yeah, you see at 35 gigahertz you have a lot more features that you can fit, and at 95 gigahertz you have a pretty good resolution. Yeah? So now if you record at these 3 different fields, yeah, then it's possible to actually find one set of parameters that fits all 3 spectra. Yeah? So it has to fit all 3 spectra. Yeah? So then you may have enough constraints to actually get reliable values of your fitting parameters. Other things that you can do is, we'll later talk more about this, pulsed excitation, advanced techniques in EPR using pulsed excitation. And what is also very helpful, particularly if you want to get some insight into the mutual tensor orientation, nowadays the programs of calculating these things from first principles is becoming possible. So DFT calculations can give you constraints on the mutual tensor orientation. So now let's talk about some applications from glass and other types of sciences. So I'll show a little bit what we've been doing and others on transition metal and rare earth ions, mostly in glasses. So transition metals and rare earth ions are typically multiple electron systems. There's not only one unpaired electron, but there are several. For example, well, titanium 3 plus has only one unpaired electron to the bank. Vanadium 4 plus also. But the chromium 3 plus has 3 unpaired electrons in the d orbitals. And so that is a spin 3-half system. Manganese 2 plus has actually 5 unpaired electrons. So the spin of this one is 5-half. Yeah? And then copper 2 plus again is a simpler case. The spin 1-half species, only 1 unpaired electron. Similar things apply to the rare earths. The gadolinium 3 plus and the europium 2 plus, for instance, have 7 unpaired electrons, 1 in each of the f orbitals. Basically, that changes the theoretical description of EPR and introduces an additional interaction, the so-called zero-field splitting interaction. Because now you have another interaction to worry about, namely the intra-atomic inter-electronic interaction. Yeah? So how for instance, in the chromium 3 plus, yeah, the spin 3-half spins, how the 3 unpaired electrons are interacting with each other. That causes additional interactions that need to be considered by additions to the Hamiltonian. Because we are not worried about, and these are mostly detected in single crystal measurements, and since we're not worried about single crystal measurements, mostly interested in glasses, we can, for the most part, really ignore this interaction. Yeah. Then, of course, we have the magnetic hyperfine couplings with nuclear spins. I'll show you some examples. And then what's special for transition metals and rare earth ions in general, we have a lot of spin-orbit coupling. Yeah? So these unpaired electrons cannot be considered pure electron spins, but there are basically they are interacting with the angular momentum. form a vector sum, but the angular momentum is partially quenched by covalent bonding. So in principle, you have to determine this either by theoretical calculations or by EPR spectroscopy experimentally. What I'm saying is G is not necessarily 2, but could have all kinds of different values. Yeah? With a few exceptions. Of course, manganese 2 plus and europium 2 plus have G equals 2 because there the orbital angular momentum is 0, because all the orbital angular momentum in the half-filled shell are cancelling out. But for most of the other species, the G will have different value. So we have, because of the spin-orbit coupling, significant G anisotropy. The line shapes are broad and structured, and parameters again need to be extracted through simulations or through additional pulsed EPR experiments. Okay. Now you might wonder, if I have unpaired electrons in my sample, can I always get a signal? The answer is no. If you see a signal, then yeah, sure, you've proven that there's an unpaired electron. But if you don't have a signal, it doesn't mean that there's no unpaired electron in there. Because it's the, in particular, because of these zero-field splittings, all of the species, the large majority of all the paramagnetic species that have an even number of electrons, like 2 unpaired electrons or 4 or 6, do not give EPR signals because the zero-field splitting is too large. So we are basically not, in the energy level diagram, we are not reaching a resonance condition at the available magnetic field strength. Yeah. So this is embodied by the so-called Kramer's rule. Kramer's rule says EPR is generally feasible on half-integer spin species, which means they have an odd number of unpaired electrons. And that's all of these species that I mentioned. For transition metals, the large majority of all candidates are shown here. For rare earths, it's these ones over here. Yeah. Another thing we have to consider are the relaxation characteristics. Titanium 3 plus is a good example. Titanium 3 plus should be an uncomplicated case, but because of the electronic structure, the spin relaxation at room temperature is very fast. And the signal becomes, because of Heisenberg broadening, of very short lifetimes of the Zeeman states, generate a very large energy uncertainty. You cannot observe an EPR signal of many titanium 3 plus species at room temperature. What you have available is temperature. So you go to liquid helium, or maybe sometimes liquid nitrogen is sufficient, and then you all of a sudden get a signal. So this is titanium 3 plus is an important species because of many applications of titania-based ceramics that are used in solar cell design. It's also an interesting ingredient in glasses. So what I've shown here in green are the ones that are uncomplicated and typically observable at room temperature, where relaxation is not imposing major problems. But the ones in black, you will also be able to see if you are adjusting the temperature, going to lower temperature. Because at lower temperature, the relaxation slows down. It is the low-frequency lattice vibrations or vibrations in the network that causes relaxation, and you're freezing them out as you go to lower temperature. So let me give you an example. Here, this is a very simple model system. It's a glass. It's a glass actually made from copper nitrate in a mixture of methanol and DMSO, dimethyl sulfoxide, frozen to 100 Kelvin. It basically is a molecular glass, and you get here the spectrum of 10 to the minus 4 molar copper nitrate solution. And here we can see what the spectrum looks like. We have to deal with the anisotropy of G and the anisotropy of the hyperfine interaction. Okay, here both of them are superimposed, but actually the tensors are coincident. And what you can see here, these four components are for the parallel component of G. This is the splitting we observe in the parallel component of G. Yeah? And in the orthogonal component of G, which of course has the higher intensity, we do not see that splitting because the hyperfine coupling is much smaller, yeah? Perpendicular to the principal axis. So this spectrum can be completely analyzed due to its favorable geometry of having this axial symmetry. So we only have to deal with 2G components and 2A components. Yeah. So copper, So copper is a good candidate for glasses also. And a lot of work of copper EPR in glasses has been done in the past. One thing one can get out of this is copper 2+ suffers a large Jahn-Teller effect. What is the Jahn-Teller effect? Basically, it's a geometric distortion from an octahedral coordination symmetry. So the copper 2+ is normally 6 coordinated, but the symmetry, the coordination is never really perfect octahedral. Yeah? And that's because if it were perfectly octahedral, the electronic levels would be T2G and EG. It would have here a degeneracy, and here as well. So this would be the three orbitals that are pointing. In the case of titanium, that would point, it would be dxz, dxy, and dy(z). And this one would be the dx square minus y square and the dz square orbitals for titanium. Yeah? We can see, consider titanium 3+ first. So we have in titanium 3+, we would have one unpaired electron, and would naturally in an octahedral environment would occupy one of these three lowest energy orbitals. Yeah? You can see now what Jahn-Teller realized is that this system can decrease its energy if it distorts. Yeah? For instance, tetragonally, if you compress along Z, yeah, then we have 2 short bonds and 4 long bonds. Then one of these, namely the XY orbital, have a lower energy, and the other two, in which the repulsion with the oxygen, with the ligands here would be stronger, would have higher energy. So we can see there's a gain in energy due to Jahn-Teller effect, which means it is all too natural that all titanium 3+ compounds will be distorted. Yeah? And they will be distorted in this way, that the octahedron is actually squished. For copper, it's just the opposite, because in copper, we are considering, then for copper, we're considering the situation of an electron hole that is different, that is the one electron that is deficient from a full shell. Yeah? So for copper D9, we only have one vacancy, and the vacancy would like to be in one of these EG orbitals. And again, we can distribute, if we distribute the 9 orbitals, the 9 electrons, in this way, we have the defect, of course, in the highest one, in the xy, x squared minus y squared. And then it shows us here the ground state is a stretched octahedron. So we have, in this case, 2 long copper oxygen bonds and 4 short ones. Yeah? So again, also in the glass we expect this. In the glass we also expect that the copper environment will always be somehow distorted. Yeah? I remind you, if the geometry were perfectly octahedral, then we would see no anisotropy. Yeah? Because that would be a cubic environment. So all copper and all titanium species are distorted, also in the glass. So let me show you some results on glasses. Now actually, when you do a Google search on copper EPR of glasses, you come to about 2,000 publications. And that's because today experts like Claudio Margon becoming rarer and rarer in the community. Many people publish some EPR results as they throw in some EPR result in addition to lots of other stuff in the glasses, and then the spectra are not competently recorded or not properly analyzed. And so you have a lot of published EPR work that has not been properly refereed and then appearing in the literature. So you have to be very careful and apply your judgment what you want to believe. So here's an example. What copper EPR spectrum could look like. Yeah? So here we have a spectra of a lead phosphate glass that has been alloyed with copper oxide, so copper 2+. Yeah? And you can see they changed the concentration of the copper oxide from 50 mole % down to 0.5 mole %. That's a lot of change. The spectra changed a lot too. Basically, these spectra here are completely useless because they're dominated by dipolar broadening, yeah? Or even at very high concentrations, even by spin exchange. So this kind of information, this kind of spectra don't give you any information because either a fraction or all of the copper ions are dominantly affected by dipolar interactions. So you have to go to really low concentrations to resolve the spectra adequately. And basically, you'd have to, whenever you want to do an EPR on a glass, you need to prepare a series of concentrations in which you're decreasing the concentration. Then you can see here, from here to there, there's not much change. So these spectra are valid, but starting from here, they are already affected by dipolar coupling. So then you analyze here these spectra in terms of G parallel and A parallel and A perpendicular and G perpendicular. And again, these spectra look a lot like the ones that I showed you on the model system of the copper 2+ solution in DMSO and methanol. And we see here again the tensors appear to be coincident, and so the electronic state of these copper species are very similar to that of our model compound. But the spectra look a little different, don't they? Yeah? And that's now because in the glassy state, you don't have exactly always the same geometry. And you have a variation depending on what else is near, what else the oxygen atoms in the glass are bonded to. Yeah? So you have to deal with this in terms of a broadening parameter. It's called an inhomogeneous broadening, a distribution of G values or a distribution of A values or both. Yeah? And then you can simulate these spectra in terms of the... Okay, here's some other examples that are useful. There's lead oxide, calcium fluoride, 60P2O5. This gives quite good, quite well-resolved EPR spectra. But you can see here, then also here, there's a little different. Huh? Now you can see here, we see splitting as well. So we can analyze this in terms of also the parameters A parallel, A perpendicular here. Here's that's from the previous system is another thing. So whenever we're talking about the distribution of G and A, we call it strain, G strain and A strain, which means nothing but distribution of interaction parameters. And the program Easy Spin that I mentioned before is a very good, can account for these kind of strained parameters. So what we learned then from these, basically that's the question that the structural chemist, of course, would like to answer. No? So let's say we have succeeded in measuring G parallel and G perpendicular. What does it relate to? And basically, people have used simplified approaches using first-order perturbation theory, and this equation is a pretty robust one. It relates, this one we can determine, it relates this parameter to parameters that define the covalency of in-plane sigma bonding and the covalency of in-plane pi bonding. This you can compare with DFT calculations, and then you actually learn that in different classes, these G parallel values are indeed different because the bond covalency is different. Yeah, so here you see some equations that relate a alpha squared to G parallel and G perpendicular. And what always enters also in this expression is the energy level difference of the between the lowest between the optical ground state and the first optical excited state, because this difference in energy is relevant in the second order perturbation theory that's being applied here. So this one is accessible from absorption spectroscopy. So we have a good connection between EPR and optical absorption spectroscopy in the case of copper, but also in the case of other transition metal ions. So it's always advisable when you want to, basically after analyzing these data, you want to come up with some interpretation to actually have a measurement of this. And if you have an absorption spectrometer at home and in your lab, then you can make this connection. And here you see some results on glass. This is a compilation of EPR parameters of copper in different types of glasses. So it's from this overview paper here. So phosphate glasses, shown over here, have a higher G parallel value than, for instance, these ones over here. That would be 7, be alumnoborate classes. So the covalency between phosphate and alumnoborate glasses are the largest difference, show the largest difference. Here's a periodic table of what you can actually, where the EPR would be useful, for what kind of elements. So again, I show in green the elemental species that are easily detectable at room temperature. Vanadium 4+, chromium 3+, manganese 2+ and 4+, iron 3+, copper 2+, europium 2, gadolinium 3, terbium 4. That's it. Yeah. Then in blue, if you go to low temperature, you can hope to see signals of those species. They're all Kramers ions. Then I also show in yellow situations when you have unpaired electrons, and you can often detect by pulsed EPR spectroscopy the interaction with those nuclei. So they manifest themselves in hyperfine couplings or in electron spin echo envelope modulation signals, which I'll talk about in a minute. You can use pulsed EPR techniques to learn something about the proximity of such nuclei to the unpaired electrons. So what are the application fields? We talk about EPR in glasses. The characterization of redox processes is very important. So chromium, I always show the oxidation state as detectable by EPR in green. So chromium 3, if there's a chromium 3, chromium 4 equilibrium, you can detect that. Vanadium 3, vanadium 4, vanadium 5, that's an important one. Manganese 2 and 4 are observable, manganese 3 is not, because it has an even number of unpaired electrons. Iron 2, iron 3, of course, is a very important application. Cobalt 2 and cobalt 3, copper 1 and copper 2, europium 2 and europium 3. Then a relatively recent application is the use of EPR to detect radiation damage of glasses that are being considered as candidates for nuclear waste disposal. So the idea is you have this nuclear waste, you need to get rid of it, and the idea is to actually enclose it in a glass. But of course, this nuclear waste is highly radioactive, and you need to study what does the radiation eventually do to the glass. Will the glass actually withstand this, this continuous exposure to high radioactivity? And it will definitely create defects. The defects will produce EPR signals, and then you can study the interaction with boron, you can study through the spectroscopy of these defects whether they're close to boron, phosphorus, or oxygen-17. So basically you can try to elucidate where exactly is the glass being weakened due to the exposure to radioactivity. Emission sites in optical glasses, that's of course for the optical community very important. Neodymium-3, europium-2, erbium-3, ytterbium-3 are the most prominent and most promising ones. Dental glass ceramics, manganese, vanadium, copper are often being used to kind of adjust a little bit of the color adjustment of artificial glasses. And yeah, you can study their bonding state using EPR spectroscopy. They're added at very, very low levels, but the levels are sufficient to actually measure by EPR. And then anion substitution in calcium phosphate is a special situation. Again, there you need to first create unpaired electrons by radiation, ionizing radiation. Then you form these CO2 minus or NO3 2 minus species that you can detect by EPR. So these are typical application fields. Here are some results on dental ceramics. Here, copper, a small amount of copper substituted hydroxyapatite, a very important ingredient of dental glass ceramics. And you can analyze the spectra here in terms of G parallel and G perpendicular. And also the A parameter from the splittings here. Octacalcium phosphate, another mineral that can be produced upon crystallization of apatitic glasses, looks very different. So we can do a phase identification through EPR. And here I mentioned that the characteristic signals of carbonate and nitrate that you would be able to produce if you irradiate the glasses with some beta or gamma, normally gamma rays. So basically there are 6 important messages for EPR, standard EPR on glasses. Low dopant levels, concentration dependent, needs to be studied. Absence of signal does not necessarily mean absence of species. You need always to test the relaxation characteristics by varying the temperature or the microwave power. Quantification is possible in favorable cases. There are special standards you can add to the sample, integrate the signal, and then compare the areas under the signals of your sample and that of the of your standard. Yeah, without simulations, you cannot publish today anymore EPR. That's at least if EPR is the main topic of your research of the paper, then you need easy spin simulations. This program is pretty much without competition in the field. Yeah, and then to relate to structure is not so easy with NMR. With NMR, we sometimes look at it and say, oh, this is this, this is this, this is this, this is methyl, ethyl, this is carboxyl. In EPR, it's always necessary, practically always, to do DFT calculations to compare then structural scenarios calculate from DFT with your actual EPR spectrum. But EPR has a lot more to offer than this by going into the time domain. And I have to cut this a little short, I believe. How much more time could I? 10 more minutes. Okay, yeah. Okay, so let's see what EPR should offer in the time domain. So time domain EPR spectroscopy uses the Fourier transform principle and the pulse excitation technique that we're using now in NMR, and Markus will talk about more in his presentation afterwards. So basically, we are operating then at a fixed magnetic field and exciting the electron spins by short radio wave pulses. Typically, we record a spin echo. Yeah? And it looks like this. But in order to get good excitation, we need very short pulses, and we need very high microwave power to cover a wide range of the spectrum, because the spectra are quite broad. And so normally we only succeed in exciting maybe, if this is the line shape, at one particular field location, we only succeed in exciting a subset of spins that have this particular orientation with a magnetic field. So what we have to do is, we have to do this in several steps. Yeah? So basically, this is the echo-detected field sweep method, which is now combining the field sweep with the pulsed excitation. Yeah? And I'll give you an example of this, and then I will wrap up the talk. And this was some work we did recently under the leadership of Claudio Magon on photothermal refractive glasses, which are basically being produced actually by a commercial company in Florida to basically create optical devices, lenses and gratings and all this. And this is due to the crystallization of a fluoride material. And you can see the composition is quite complicated. We studied 6 different samples by EPR. This one is, what I should say is, this particular crystallization process only takes place upon exposition to laser irradiation, to optical irradiation. And so the unexposed glass has this particular composition. Why does it have to be so complicated? Because that seems to be what Oleg Glebov and his wife, by many trial and error techniques, found the optimum composition. And then B2 is now a UV exposed glass that shows these periodic periodic density and refractive index variations that you need for the optical application. And then what was found is that it works particularly well if you have a little bit of antimony, cerium, and tin, preferably all of it, also present. And that was always kind of a little bit magic. Why we need these dopants there for facilitating the crystallization, facilitating the glass. So the optimized composition always contain this. And what exactly these dopants are doing, we try to address by EPR spectroscopy. So then we prepared these 6 samples. Also silver needs to be present. So we prepared these 6 samples, and 3 of them were UV exposed, and 3 of them were not. And the ones that were not exposed gave no EPR signal. The ones that are most important, however, are B5 and B6, which contain these dopants, again, before and after. But these also contain silver, which is already here present in B4. So what did the EPR then look like? First of all, this is the sample that was most interesting and most intriguing, the EPR spectrum of the exposed glass B6. So this one has everything in it: silver, tin, antimony, and cerium, and it was also irradiated with UV. Here's a spectrum that was recorded at 10 Kelvin, and it looks very adventurous, very exciting also. First of all, I don't show it here, but the glasses that did not contain antimony tin, and basically the glass that was shown over here at B2, yeah, this is the standard glass. That one showed only the broad hump here. It did contain cerium. So this broad hump that we're seeing here in the pulsed EPR spectrum is just due to the cerium 3+ dopant. The cerium has an F 5/2, 2F5/2 state, 1 unpaired electron, cerium 3+, and because of a large spin orbit coupling, we do have this very broad line shape. But more interesting are the sharp features here, and we could clearly identify them as being the interacting species with antimony. Antimony has two isotopes that have nuclear magnetic moment, 121 and 123, and they have spin quantum number 5½ and 7½, and 123 has a smaller nuclear magnetic moment, so the splitting actually is smaller. So here you can see in the simulation, the simulated spectrum, considering the interaction, the hyperfine coupling between these two nuclei and the unpaired electron. Yeah? Adjusting the ratio of the nuclear magnetic moment, taking care of the natural abundances of antimony 121 and 123. And the simulated spectrum, as you can see, shows an excellent agreement with the experimental data. So the antimony plays a very important role in this process. Yeah? So here we have the situation again, the spectrum that I just showed you before. And the one before exposure to ultraviolet shows a very weak. You can also guess there's something there, but it's much weaker. This is because we always have a little bit of UV exposure in the lab due to the neon lights or the sunlight. So, but upon UV exposure, the signal becomes much bigger. And then when you do thermal treatment, then it goes away. So then basically this antimony is now species probably getting oxidized, and then is no longer the sp4+ species that it would have to be to give a signal like this. So the mechanism we think is the following, at least for the initial process. The cerium 3+ partially goes to cerium 4+ and liberates an electron upon UV exposure. That electron is captured by the antimony, which is normally in the 5+ state, and goes to the 4+ state. This one is then the source of our EPR signal. Yeah? But then also then in part actually the antimony 4+ can then form react with silver plus that is also present in the glass to cause a reoxidation, and then we form silver nanoclusters. This happens upon thermal treatment, so when heating this material. And in fact, the silver nanoclusters can be detected by optical spectroscopy. So basically, this is something observable, but principally only by optics. And it seems to be these silver nanoclusters that facilitate the nucleation of sodium fluoride that causes then the refractive index variation. Although the current discussion also involves the idea that maybe the nucleation of NAF is just a side product, and it's actually the silver clusters that are imparting the special optical properties to the glasses. Yeah. Okay. So maybe then very briefly, electron spin echo envelope modulation. Yeah. I mentioned before, we can detect nuclei that are in the vicinity of unpaired electrons by this particular process. The electron spin envelope modulation basically utilizes forbidden transition. So the allowed transitions in the two-spin system are shown in green. These are the allowed EPR transitions in this two-spin system of unpaired electron and the nucleus. Here are the nuclear transitions, and the red ones, where the nuclei are actually changing spin state, orientational state, are normally forbidden. But under the effect of the nuclear hyperfine coupling, they become partially allowed, and then they cause modulations in the on the electron spin echo. Yeah? And this can be detected by pulsed method. The electron spin echo, which is normally just two pulses, a pi pulse, a pi over 2 pulse, and a pi pulse, and then you record an echo. If there's no interaction with nuclei, the echo would be simply exponential, decaying as a function of pulse spacing between the two nuclei, between the two pulses. And however, you can see over here, if there's an interaction with nuclei, you see these modulations. And you can basically analyze this by stripping off that exponential decay and then basically do a Fourier transform here. And in, just very briefly, at least as far as glasses are concerned, what you get then is the Zeeman frequency of the nuclei that these unpaired electrons are interacting with. So in this case, it was the case of an alumno-borate glass. We see the Zeeman frequency here of boron 10 and boron 11. And one can also observe aluminum under special conditions. Basically, this is chosen as a condition where we do not see aluminum. It's a matter of the spacing between the two pulses. And basically what we have, and I think Markus will talk a little bit more about this in his contribution, we have applied this method to characterize rare earth environments in fluorophosphate glasses. And basically there was a threefold strategy. First we would, so we were simply interested in the question, the rare earth ions, are they interacting with phosphate or with fluoride? What is the coordination of the rare earths? One way to approach this is to simply substitute the rare earths by something diamagnetic, like scandium and yttrium, and do NMR of this. Another way would be to look at how the paramagnetic ions is affecting the nuclei in their vicinity. And the third method, the third approach would be to actually look at the EPR signal of the unpaired, of the paramagnetic species itself. And ytterbium and neodymium are the ones that are most attractive for this and most suitable. And this one, the signal of this ytterbium 3+ is the one we have used most. This spin echo will be affected by the Zeeman interaction, by the hyperfine interaction with nuclei that are close to this unpaired electron, to this unpaired electron species. Yeah, and then we have analyzed this and basically found that the ligand distribution between phosphate and fluoride depends very much on the system that you study, but certainly what one desires is generally that the environment of the rare earth is dominated by fluoride, and we were able to find a suitable system on this, and the references are shown over here. And in the suitable system, the EPR spectrum will always look the same because the coordination is dominated by fluoride. And so what you see here is basically here in this system here. This is the optimized composition. What you see here is that we have changed the fluoride to phosphate ratio of the glass. So we changed it systematically, but the EPR spectrum always looks more or less the same, showing that there's a constant environment. Ytterbium prefers the fluorine. But in other systems, it's different. For instance, here in the fluorophosphate with aluminum, you see a big change with composition. And with this, I will stop here and entertain questions or give Marcus the possibility to acrescentar. Yeah. Thank you. Right. Yes, in fact, I should at least show the acknowledgements here, the collaborators, very important, in particular highlight Claudio, who didn't make it to the group picture here. Yeah.
Questions? Well, I have one, Helmut. We have seen this morning several talks regarding niobium in glasses. Our group is also interested in niobium in glasses because niobium is a very interesting ion, and niobium plus 5 does not impart any color to glasses, but niobium plus 4 and plus 3, they impart color, which are in many cases undesirable if you are working as optical glasses. So, but the key thing is that normally niobium glasses are used in large quantities, few percent. However, I can have like 5% mole of niobium oxide, but only say 0.5% of that niobium will be in the state plus 4. So can we still use EPR in that case to check for the existence of niobium plus 4?
Yeah, the niobium 4 plus species would be quite dilute. The only problem is that you have most of the time from what we found is the niobium is clustering. So we may have only one niobium 4 plus, but the electron might be quite mobile to jump to other niobium species in their surroundings. And then this will affect the EPR signal. But one can try to slow down this by going to low temperature. So my prediction would be that niobium EPR, yes, should be possible if you go to liquid helium temperature.
To liquid helium.
Niobium plus 4. No?
Plus 4, yeah. Good. We have to try because we are having these problems with colors in optical glasses that are not desirable. Color absorption is not desirable. Any other? Yes, please. Could you please again repeat your name, etc., so we get to memorize all the names along the school?
I'm Ecem Kırmak-Yamaç. I'm a PhD student at Alfred University. Thank you so much. This quite meaningful presentation. My question about EPR spectroscopy, you mentioned that we can observe relaxation behavior. So we can observe or we can measure experimentally this behavior because it's very hard to observe and hard to experimentally analyze us for behavior, relaxation behavior. So could we do this with EPR?
If there yes, there are techniques to measure spin lattice relaxation times and spin-spin relaxation times. Both relaxation times are in principle measured preferentially using pulsed EPR methods. Yeah? Pulsed EPR methods.
And follow-up question, sorry for that. Is there any strict or borders for measure these methods? For example, only use some kind of elements or atoms, or we can use all the elements?
Didn't quite get the
elements.
The elements, yes. Yes, then go back to this periodic table here. Okay, so basically, yeah, the ones in green are the easiest ones to measure these kind of relaxation characteristics because their relaxation times are pretty long already. Yeah, so that basically allows us to measure them at room temperature, and then as we're going down in temperature, the relaxation times will increase. Yeah? The blue ones, yeah, maybe if you find a suitable temperature range. There's also a limit, in particular at very low temperatures, they might be too long to measure. So it's depends on this. Yeah.
Thank you so much.
Yeah. No, there are theories. Basically, there's a so-called Orbach mechanism that predicts temperature dependence on the of the relaxation rate, the relaxation rate with T to the 7. Yeah? So it's a very strong temperature dependence. So there are simple models theories that predict how relaxation times should depend on temperature. Yeah. But I would, there's one more here.
There's a question here.
My name is Philipp Keim. I mostly do NMR at the University of Münster. I have, regarding the element table you're showing, a question. Just why is it not possible for many of these elements to observe the hyperfine interactions, such as lithium or carbon, for example?
Well, the hyperfine interaction should be observable if the relaxation, it depends. It's often the question of resolution. No? So if the G anisotropy in many cases is much larger than the A anisotropy, and then the resolution doesn't allow you to observe these separate peaks. So in the case of antimony and copper, I've shown you examples where it's possible, but you could see that for the copper, it was only possible, let's see, over here, was oftentimes only possible to resolve the interaction in this part here, in the parallel part. In the perpendicular part, the resolution isn't good enough. Yeah? So, yeah, you can get better resolution, lowering the temperature, or making the magnetic species more dilute. And then, but yeah, there are certain limits also, because you can see, in order to record this spectra, you need to modulate the magnetic field, and the modulation amplitude will limit your resolution also. So it's sometimes really a trade-off. But it's possible typically to observe always the hyperfine coupling under certain suitable conditions if the nucleus belongs to the same atom that carries the electron spin. Yeah? So if, in the case of the antimony and here the copper, we can observe the coupling between the copper 63 and 65 nuclei on the copper carrying the unpaired electron. But in certain cases, many cases actually, you can also observe the hyperfine coupling with a directly bonded nuclei like fluorine and so on. Yeah? So that's called then the super hyperfine coupling. But yeah, there of course you have more demands on the resolution. Yeah.
Thank you.
Hi, my name is Jacob, and I'm from University of California, Davis. So I was under the impression that EPR is most informative. I think you said one of your takeaway points for low concentrations of dopants. But then in the echo decay and modulation slide, you were showing data about boron for aluminoborate. I was wondering if you could elaborate on why that was possible there.
Yeah. Yeah, yeah. So this was a typical example you mentioned. No? Yeah. So in this case, what we're actually looking at, it's not showing here, so I'm glad for this question. These classes were doped with ytterbium oxide, yeah, or ytterbium fluoride now. So and only at a level of 0.2 mole%. Yeah. And so because of this, and this ytterbium is the source of the unpaired electron signal, and the ytterbium near in the vicinity of boron, we estimate it could be somewhere between 5 and 8 angstrom, would give then a modulated signal that gives rise then in the ESEM a signal to give a line like this. Yeah. So yeah, the observed species is not unpaired electrons on the boron directly, but it's boron near ytterbium 3+ dopant.
So it's like adjacent structures that you're looking
Adjacent,
at.
adjacent. But the method is quite sensitive in distance. I have another picture to show this. So this way I get to show everything. Yeah? So we see here NMR and EPR, what they can do. Yeah? So magic angle spinning NMR is good for the first coordination sphere. Dipolar techniques like REDOR, Marcus will talk about it, is good for the medium range order. If you're only interested in the atom itself, then you can do the standard EPR. But if you're interested in what's in the vicinity of, I'd say, 5 to 8 angstrom, then this ESEM is a quite a useful method. So the distance ranges are complementary. It's good to apply both methods.
Thank you.
Thank you.
Okay, well, let me thank Helmut again for this excellent lecture and invite you all for our coffee break and continuation of the poster session downstairs. And also, because of our cocktail party tonight, I urge you to be back by, say, 4:05. I'm giving 5 minutes more. 4:05 back here. 4:05 back here. Thank you, Helmut. And we have an NMR lecture by Marcos Oliveira at 4:05 sharp. Cidade, sabe? Mas é ao lado da fábrica da Volkswagen. É ao lado. Se você chegar
ele essa. Yeah, I did the API on the new.
Hello? Okay, so although we still have some people down there at the coffee break, I think we should start so we don't get too late here with the program. Thank you very much for being here. I take the opportunity to introduce myself while the people are walking in. So I'm Professor Andrea de Camargo, also one of the speakers of this school. And it's my pleasure now to introduce Professor Marcos de Oliveira Jr. He is a professor here at IFSC since 2019. He is also an expert on NMR spectroscopy with focus on solid state. And before he was hired as a professor here in this university, he spent 2 years working in Darmstadt, also on an NMR group. So he's quite skilled, and he's going to be talking about NMR to characterize glass structure. Welcome, Marcos.
Okay, thank you, Andrea. So now after the lecture by Helmut that was speaking about the spectroscopy that uses the spin of the electron, I will now speak about NMR that uses the spin of the nuclei to get information about structure. Then, let me turn this on here. Yeah. Then my talk will start with a short introduction. After the historical introduction Helmut did, I decided to delete some slides, so I will skip the historical introduction and start with the phenomenon itself. I'll speak a little bit about the NMR interactions that are relevant for solids, because we are speaking about studying glasses that are solids. And then I'll show some examples of techniques and results and how we can get information, structural information from NMR. Then this is my background. So I've walked through many fields in chemistry and material science. So starting from organic, inorganic hybrids, and then moved to the glasses. And nowadays I try to put these two together to study hybrid glasses. But my main expertise is on the spectroscopy techniques, such as the nuclear magnetic resonance that I will speak about today, electron paramagnetic resonance that Helmut spoke a few minutes ago, and dynamic nuclear polarization, that it's a technique that kind of takes advantage on both the nuclear and electron spin interactions. So a little bit of the introduction. So as Helmut said, we can associate to the angular momentum, or spin angular momentum of the proton in this case, magnetic momentum. So we can think about the proton as a charged spherical particle that's spinning, and then it has an angular momentum, and since it has charge and is spinning, also has a magnetic momentum. But the problem is it's not a sphere and it's not spinning. It's a quantum entity, so we try to make this classical analogy, but nature is not like that. So quantically, we can speak about the relation between the magnetic moment and the spin operator. So it's given by this constant here, we call the zero-magnetic ratio. This depends on the isotope we are studying, so this makes NMR selective. You can select to which isotope you are going to look at each experiment. The constant Planck to give the units, and the spin operator, that's an angular momentum operator. It has all the algebra of angular momentum in quantum mechanics. And associated with it, we have a magnetic moment. That's the main property of the nuclei that I'm going to discuss now. So mandatory for NMR is that the nuclei have a spin different from zero. So here I put some examples in the periodic table of the nuclei that has, or the isotopes that has spin 1/2, for example. You can see that for only some isotopes are active in NMR. For carbon, for example, the most abundant carbon-12 is not active in NMR because the spin quantum number is 0. So we have to deal with the carbon-13, that's about 1% abundant. So these are the ones that have spin 1/2, and I will limit the introduction of the phenomenon of NMR to the spin 1/2 in the beginning, and I'll speak a little bit about the other spin quantum numbers in less detail afterwards. So here are this nuclei that have the isotopes that has spin quantum number equal to 1, integer spin quantum number. So, and if you look to the colors here also, the strong colors are the species that have high resonance frequency. So they are, if you look only to this parameter, they are good to measure. And the lighter ones, they have a very low frequency, so they have some limitations some equipment limitations. And here are the half integer spins. They are the majority of the periodic table. So just to give examples here, the shapes of the symbols here, they give the spin quantum numbers. So this is just to give an overview on the different isotopes we can find in the periodic table. And this table here shows, you can find an isotope, it's active in NMR, but doesn't mean that you can get structural information from that isotope. So this table here is a compilation of the good nuclei to do NMR, so the black ones you can do without any problem. And then when you go down the scale here, things get more difficult, and then you need special techniques or special theory or quantum computations to get information about your structure. And in some cases, it's still not possible with the technology we have. So again, we have a magnetic moment in the nuclei that are active in NMR. And the main interaction is between this magnetic momentum and the magnetic field that's applied by the spectroscopist. So we have a big magnet there, I will show it here. We put a magnetic field there, and then we have a Hamiltonian of the interaction between the magnetic moment and the magnetic field that's applied. So usually, to make things easier, we call the z direction the direction of the magnetic field. Then this Hamiltonian translates to this relation here. So the important operator here is the operator Iz. And this operator Iz, so we can translate all these constants to a single constant I will call omega 0 for now. We are going to see the meaning of this omega 0 in a few slides. And then this Iz has a orientational quantization, so it has these properties here. You cannot have the eigenvalues of this operator, they cannot have any value, but they need to be they are limited to the spin quantum number, so -i, -i+1, and so on. So we would have 2i plus 1 levels in this quantum system. If we go to the easiest system, that's the spin 1/2, the first periodic table I showed there, then we have m assuming values that's minus 1/2 and plus 1/2, just as in the case of the electron. Then things get easier. We can translate this Hamiltonian to matricial form. Or if you think about vectors, we have the spins pointing in the direction of the magnetic field, so they have preferential energy to be in this state here, or the antiparallel state that has a higher energy. So we have a break of the degeneracy here. So we have 2 energy levels, and then we can start doing spectroscopy. And then, since we have energy levels, now we can promote transitions between the levels. And the difference in energy here is corresponds to this omega 0 that's showing up here. That's equal to the gamma, the constant Planck, and the B0 value. So it depends on the magnetic field you are applying and on the isotope you are measuring. That's defined by this gamma value here. So we have populations in these states that are given in the equilibrium by the Boltzmann distribution. So, of course, we will have more spins in the lower energy level than in the higher energy level. But for NMR, this difference in energy is so small, this is much smaller than in the case of EPR, that we have very few spins, very small difference of population in the upper state and the bottom state here. Then if we take an example here, for 20,000 spins, we have a difference of only 2 spins, giving our net magnetization. That's what we can measure. So NMR has relatively low sensitivity when you compare to other spectroscopies. And the intensity of our signal will depend on this n factor here, the number of spins we have in the sample. So it's quantitative. The NMR gives a quantitative result. Depends on the magnetic field and also on the temperature. Okay. Then, saying like this, now you have 2 energy levels, you have populations, and then the spectroscopy is done by promoting this guy to the upper state, and then when it goes back, it emits a radiation, and when we detect this radiation. It would be easier that way, but it's not like we do the experiment. The experiment's done a little bit differently. We have this paper published here in Concepts in Magnetic Resonance in '89 because they were worried about the biology community that were treating NMR like optical spectroscopy, and then they were getting wrong impression of the technique. So now I will try to explain how we actually do NMR, and I hope that it's understandable for everyone. Because I think by now you have realized from NMR field, we like to show how difficult NMR is. It's our pleasure to do that. So I put this animation here just to show when we put a magnetic field. So initially we have all spins pointing to any direction. So if you put in a magnetic field, we have a preferential orientation. And then when we take the statistics of all the guys that are pointing up against the guys that are pointing down, what we see here is that they sum up to give a net magnetization. So it's a macroscopic magnetization, and then we can treat it by classical analysis. So this magnetization comes from the sum of all magnetic momenta that we have in our system. And if we sum up all these spin operators together with the constant Planck, what we have here is an angular momentum. And from classical theory, we know that from the interaction of the magnetization with the magnetic field, we create a torque. And then, of course, the torque will be responsible for a change in the angular momentum. So the variation in the angular momentum is just equal to the torque. But the J is related to M, so we have a differential equation to solve that gives us the motion of the magnetization. It's a relatively easy equation. I think we are all engineers and chemists. So to solve this equation, First, we put this magnetic field in the z direction, calculate this vector product here, and then we can find all the components of these derivatives here. So we have components x, y, and z. So if I take the derivative of x, I take y. If I take the derivative of y, it's minus x. And the derivative of z is 0. So this can be nothing more than a vector precessing around the magnetic field. So it's describing a circle in the plane here, and the magnetization in the z direction is constant. So, and the omega 0 that goes in the solution here is exactly the same gamma b0 that I showed before. That's the separation between the energy levels. It's not a coincidence. It has a reason. And then this is what we call the Larmor frequency. So this is the frequency the nucleus would have if it would be isolated in space. And then, but if we leave this magnetization there, I showed that it's pointing the z direction in the beginning, and the process is around z. So if you leave it there, it will stay there forever, and you have no experiment. So we need to remove it from its equilibrium. And we do this by applying an oscillating magnetic field that's perpendicular to the magnetization. And then, instead of having now only B0, we have B0 plus a B1, where B1 is the field we are applying with this coil here. So B1 that has this shape here. It has an amplitude, and then oscillate as a cosine. Then if we put this in the equation, then we have this equation here. Now it depends on time. It's harder to solve this because you have this time dependence. Then to get things easier, we move our system to a rotating frame. Now we are in a frame that's rotating with the same frequency that we are using to irradiate our system. Then the equation gets easier. Then we can show that gamma B0 times this magnetization shows a guy precessing around the B0. So if it's precessing around B0 with frequency omega 0, and I spin my system with frequency omega, it's easy to show that now I have this gamma B0 plus omega here. And then the time, so we don't have a time dependence here, and here neither. Then we can put this equation together. Aqui. We can put this equation together. Then we get a simpler equation where we can see here an effective field. So now the equation looks just like the same one we had before, but instead of precessing around B0, now our magnetization is precessing around an effective field that has this component in Z and the B1 component in X. And then the resonance part of the name of the technique comes here. We can select the frequency that we are irradiate our sample here. So this omega can be chosen to be equal minus gamma B0. That's our Larmor frequency. Then the equation gets much simpler. We have only a field B1. And in this resonance condition, the magnetization is flipping around the B1 field. And then this is the most effective way of moving the magnetization from its equilibrium state. So if we wait, and the precession frequency, remember it's given by this prefactor here. So it precesses with a frequency that's equal to gamma B1. So if you wait time enough for this magnetization to be on the plane, then, and turn the radiation off, then we have what we call a pi-half pulse. And then if you leave the magnetization here, now it will try to turn back to equilibrium. And during this evolution back to equilibrium, we can detect our signal. So this is more or less what I explained. So in the beginning, you have here the precession around Z. Then you move to a rotating frame. The magnetization is freezed in the rotating frame. And then when you turn on B1, magnetization is spinning around the B1 field. So here it's the representation of what's happening with the spins while we are moving the magnetization. So this would be a pi-half pulse. And when it comes back to equilibrium, it has two processes. The first process is the T2 relaxation. You see that they are losing coherence, and then this makes the net magnetization go to 0 in the XY plane. And at the same time, another process occurs. So this is called the T2 relaxation, or spin-spin relaxation, or transversal relaxation, because we are losing transversal magnetization here. Here it's another process, because while we had equal distribution of spins up and down after the pulse, now they start to go back to the Zeeman, to the Boltzmann distribution, and then we recreate magnetization in the Z direction, in the direction of the magnetic field. And this is called longitudinal direction, because it's in the direction of the magnetic field. Or T1 relaxation, or also spin lattice relaxation. So if we put all together, we have our NMR experiment. So you start with a pi-half pulse, and then your system starts to evolve. This magnetization is spinning around B0 field, this giving an oscillating signal. And this oscillation decays because of relaxation. Then we have a signal that has this shape here. And this is how we represent the pulse sequences we are applying. So from now on, I will not show vectors anymore, because they are not always useful. We have schemes like this, so we wait a little time here to get magnetization in the Zeeman population. Then we apply a pi-half pulse and acquire our signal. And then to get the frequencies that are within this signal, we apply Fourier transformation, then we have our spectrum here. This is how the equipment looks like, more or less. We have a big magnet. This magnet is a superconducting magnet, so we need liquid helium temperatures to keep the superconducting coil that's inside here. Then it has some layers just for keeping the helium liquid. So we have liquid nitrogen, some vacuum layers. So it's a thermal bottle. And then our sample is put inside the coil that we are using to excite the spin systems. And this is placed inside the magnet by a probe. And this probe is displayed here. You don't need to see it in detail, but it's a radio frequency circuit. So it's a resonance circuit that's here just to put the right frequency there on the coil where we need the radiation. And here are some examples of the sample holders we use, because usually when people are collaborating and ask for NMR experiments, they are always asking how much sample I need to send, how many milligrams. I never know how many milligrams. But these are the sizes of the sample holders, so you can know more or less how much sample you need. So this is the general experimental setup. So what we have in the spectrometer, that's sending the signal to the probe and getting it back also from the probe. We have here a transmitter that's putting together our pulses in the right frequency. So they send this signal to the sample, so I put here an antenna to represent this radiation. The sample is radiated, it has a response. In this response, we have information about the Larmor frequency, that's the same one we use to excite our sample, plus the singer here is our signal, our meaningful signal. And we want only the singer voice in our final spectrum. So in the receptor, what we do is the same thing that the radio receiver does. We subtract the carrier, and then we get only our meaningful signal. Because the Larmor frequency we already know, so we don't want more information about that. And then here comes the interesting part, because if it would be only the Zeeman interaction, then we would have only information about what's the nature of this isotope we are measuring. But we have more interactions in NMR, and they are the interactions that makes NMR a technique that's good for structural characterization. So we have the dipolar interaction, that's the interaction between two spin magnetic momenta. So we can get information here about distances, for example. The J coupling is an interaction through the electrons in a bonding. Then it gets information about bonds. The chemical shift gives information also. The chemical shift I will explain in detail, so I'll not explain twice. So it gives information about bonds and also about the geometry of these bonds, the environment of the observed species. And then the quadpolar coupling, that's also sensitive to the electric field gradients in the sample, so it's also sensitive to geometry. So speaking a little bit about the interactions, the first interaction is the chemical shift interaction. So in this interaction, we have our electronic cloud here. The electrons are moving inside this electronic cloud. And then we put a magnetic field B0 there. What happens is that you have charges moving in a magnetic field. So you create an induced magnetic field in this electronic sphere. And this induced magnetic field affects the resonances of the nuclei. So we can get information about these electron clouds here. So this is an example for a benzene ring. You can see that if I place the magnetic field in this direction, I'll have one behavior for the induced magnetic field. But if the magnetic field is placed in this direction, you can imagine that the behavior will be much different. The induced magnetic field will be much different than in the other position. So this induced field here relates to the applied magnetic field by a tensor. So you apply the magnetic field in one direction, the induced field can be in other direction. So they have a tensor relationship. In few words, the net frequency you are going to observe comes from the Larmor frequency plus the frequency corresponding to this induced field here. And then when we open up this tensor, take only the important parts, we end up with this equation here. So this is the frequency of our system when we are subject to this chemical shift interaction. So you see some angular dependence here. This angular dependence is the dependence between the molecular frame and the magnetic field. Like the example of benzene, you imagine that you have different induced fields, you have different frequencies. So the frequency depends on the orientation of the molecule relative to the magnetic field. And these are ways of representing the main values of this interaction here. So you can represent by the principal values of this tensor, that's x, y, and z components, or from these parameters that gives information about symmetry. So we have the isotropic chemical shift, that's the mean value of the principal values. This is what you observe if you do a liquid state NMR. We have this delta parameter, that's our anisotropy parameter. So if delta is different from 0, we have some anisotropy, so makes a difference when you move your molecule. And eta is an asymmetry parameter. So if eta is 0, we have the axial symmetry. If eta is different from 0, then we have a rhombic symmetry. Then, since for different orientations, we would have different frequencies. So this is the molecular frame, so relative to the magnetic field. So we can see that we have different frequencies for x, y, and z. So in a glass, before doing the experiment, we smash the glass, we make a powder, so we have all the orientations possible. And then when you do the statistics, a static line in NMR for spin 1.5 will look like this. So we have contributions from orientations x, y, and z, and all orientations that lies within these three main orientations. This is an example for phosphates, for example. I think we have aquí. So for Q3 species, we have an axial symmetry. The same applies for Q1. The difference is that for Q3, we have a delta smaller than 0, and for Q1, we have a delta larger than 0. For Q2 species, we have no symmetry at all. We have a rhombic geometry, so eta is larger than 0. And for the Q0 species, all directions they are the same. So we have an isotropic case. And then the eta is equal 0, and the anisotropy parameter is nearly 0. So from the static line shapes, you can decide which phosphate species you have. Problem is that in glasses, we have a distribution of these parameters. And also, we have sometimes all the species showing up together. Then the static spectrum, it gets hard to resolve something. The second interaction that I will speak about is the dipolar interaction. So it comes from the dipole-dipole interaction between two magnetic momenta. The important here is the internuclear vector and its orientation with the magnetic field. So I jumped all the complicated theory. The full Hamiltonian would look like this. But we don't need to work with the full Hamiltonian because this interaction is small, usually is small in the systems we study. It can be treated as perturbation. Then we keep only parameters that are relevant for perturbation theory, and we end up with these Hamiltonians here. So the main interaction here is between IZ, SZ, where I and S are the two spins that are interacting with each other. The heteronuclear interaction has this shape here, and the homonuclear interaction has this additional factor here that we call flip-flop interactions. But in both cases, we have the same angular dependence that we see for the chemical shift anisotropy. And then keep this dependence in mind. It's the second Legendre polynomial. And this term here is named flip-flop. And this is the main difference between heteronuclear interaction and homonuclear interaction. I'll treat only the heteronuclear interaction. I'll leave the homonuclear interaction for another lecture, because it's not the most important one for glasses. I can speak about the reasons if someone asks. So in the Zeeman, if we have a two-spin system, then we have a sum of angular momenta. We have 4 energy levels. 2 of them are degenerate, and then we have 2 other levels, 1 minus 1 and 1, 1. The nuclear transitions are this one and this one. And then when we add the dipolar coupling, then we break this degeneracy here. And then we have now more transitions here, that we have at least 2 possible transitions. Before they had the same frequency, now we have 2 different frequencies. And because of this term here that tells how this internuclear vector is oriented relative to the magnetic field, we will have also anisotropy. So when we change the orientation of this internuclear vector, we change the frequency, then for heteronuclear coupled systems, we have this powder pattern, as we call. What happens in the glass is that we have a mixture of them. So if we put some together, we have this line shape. If we put many of them together, we have a Gaussian line. And then we cannot have information anymore about these splittings here, but we can have an overall information about the average dipolar coupling we have in our sample. And this translates as the second moment of the dipolar interaction. So the second moment is proportional to all these constants. Important ones are the spin quantum numbers, the gyromagnetic ratios of the 2 nuclei that are involved in this interaction. And you have here an information that has to do with the distances, the average distances, nuclear distances. So this brings us structural information for the characterization of the classes. So the last interaction is the scalar coupling or J coupling. I put in Portuguese here. It's the interaction that comes, it's promediated by the electrons that are in a bond. So this nucleus causes perturbations in this electron that transfers to the other nuclei, and then we can have splittings of our energies here. I'll not speak too much about these splittings here, but this is a case where I have 2 spin 1/2 interacting. Each of these lines breaks up in 2, and then it's forbidden to have transitions of both spins together. Then we have only 2 possible transitions. Then we have 2 lines. When we have more spins interaction, then we have a multiplet. If you have an interaction with a quadrupolar nucleus, like in this case phosphorus with copper, then we have 4 possible transitions. Then we see this kind of spectra here. But what happens in glasses is that you have a distribution of these J couplings also. And usually what we see is a broad line. So we cannot get direct information about J couplings from hyperfine splittings in our spectrum. So I thought it was the last one, but we have the quadrupolar interaction. It's only present when the spin quantum number is larger than 1/2. Then we have our nucleus is not spherically symmetric. It has a distribution of charges. So it has a quadrupolar moment. And this quadrupolar moment is linked to the spin orientation. So if you change the orientation of the quadrupolar moment of the nucleus, you change the spin together, then it brings us an NMR interaction as well. So it comes from the interaction of this quadrupolar coupling moment with the electric field gradients in our sample. Then it has this appearance here. I will not open up the equations here. We are running out of time, but I want to show the effect in the spectra and in the energy splittings. So if we take a half-integer nucleus, we have these splittings here, and this constant omega q is given by this equation. And look at what we have again, the same polynomial, the second polynomial of Legendre. So this gives us, this is relative of the orientation between the quadrupolar moment tensor and the magnetic field. So if we look to a spin 3/2, we have 3 transitions, 3/2 to -1/2, 1/2 to -1/2, 3/2 to 1/2. We call this one here the central transition for obvious reasons. And then you see here that if you look closely, we also have anisotropy. We have the same line shapes that we are observing in the other cases that comes from the statistic of orientations in our sample. So if this VZZ is pointing perpendicular to the magnetic field, we have one situation, parallel we have another situation. This happens for more than one transition, so we have this interesting line shape. It would be hard if we had only this, but then we have to treat with perturbation theory in second order as well. When you go to second order, we have further splitting of the lines. You see that before, the central line didn't change, so we have a sharp line for the central transition, but now the central transition is also affected, and the relation, angular dependence, goes with the P2 of cosine theta again, but we also have another Legendre polynomial here, that's the P4, so we have another angular dependence here. When you look to the shapes of the spectra, they can have all types of shapes depending on the spin quantum number and on the quadrupolar coupling parameters. And in glasses, we may have all of them together because we have a distribution of electric field gradients in the sample. We also have a distribution of quadrupolar coupling interactions, and what we usually have is a broad line. This is just to take all cases. For spin 1, we don't have a central transition. So already in first order, we have a complex line shape. So let's move to the applications before you start to sleep. No? So for glasses, we can separate some aspects of glass characterization. The first one is that we can measure mobility by NMR, so we can measure mobility of the ions in, for example, ion-conducting glasses. So I put only one example here, where you can see a lithium spectrum varying as a function of temperature. So for low temperature, we have a broad spectrum here that comes from dipolar interactions. And when you start to heat the sample, this lithium starts to get some mobility. This mobility averages out the dipolar coupling. And then we have a sharp line. And from the onset of this motional narrowing here, we can get information about mobility in these systems. Other thing that we can investigate is the distribution of network modifiers in the glass. So we can see if we have clustering, if we have statistical distribution, and so on. And before explaining that, I'll explain a main experiment in the techniques I'm pointing out here. That's the spin echo. So the spin echo is relatively easy to understand with vectors. So we have a spin pi-half pulse. Our magnetization goes to the xy plane. And then from the T2 relaxation that I showed, we start having coherence loss here. So some guys are moving clockwise, other guys are moving counterclockwise. And then if we apply a pi pulse, this guy that was moving counterclockwise here, you keep moving counterclockwise. So the guys are opening here. I apply a pi pulse, they turn like this. So this strong line here goes up and keeps going the same direction, so we have a refocusing of our signal, and then we have what we call an echo. And then if we do this experiment, varying the time between these pulses, what we see a decay here that will be like this for liquids, but for solids, we have a Gaussian decay, and this decay is mainly dominated by homonuclear dipolar coupling. Because to have a refocus here, in this period here, you need to have the same Hamiltonian as you have in this period here. But then you have two neighbors of the same species. This guy is filling the field of this guy up. But then you apply a pi pulse, and then both are inverted. Now the Hamiltonian that this guy is observing is changed. So you don't have the refocusing anymore. And this gets worse with time. Then you lose the coherence of the echo. And this coherence loss goes with the second moment, the same one I showed before when I was speaking about dipolar coupling. It's the average dipolar coupling in our system. So this is an experimental curve. So if you look at the intensity of the signal as a function of this time, we see a Gaussian decay in the beginning of our curve. We can get second moments from this decay. And here are examples for glasses, for model compounds containing sodium species. So you see that we have a very linear correlation between calculated values for the crystalline structures and the experimental values. And when we do this for glasses, here we have two examples. We have sodium silicate glasses and sodium borate glasses. For the borate, we have a linear variation of second moment with composition, which means that this distribution is statistical. I'm just putting more species there, the interaction is growing linearly. But for the silicate glasses, what happens is that we have a deviation from this linear behavior, and this indicates that we are having clustering of sodium in this system here. The same thing happens for lithium, but to detect the lithium, we need a different type of experiment. That's called the CDOR experiment. The CDOR has the same idea, but now we are treating heteronuclear dipolar couplings. The species are not the same anymore. So if they are not the same, when I apply pi pulse for one guy, the other guy doesn't feel it, and then the echo is refocused. The contribution from this interaction is refocused here. So this echo doesn't decay with the heteronuclear dipolar coupling. So what we do, we invert it. And then now it decays with the heteronuclear dipolar coupling. We already know that this decays with homonuclear dipolar coupling. Then if we take the difference, we can have only contribution from the heteronuclear dipolar coupling. And then this goes with a Gaussian again, where we can take also the second moment. I put the equation again here, and we can get information about this distribution of species. So we can do this, for example, with two isotopes of lithium, lithium-7 and lithium-6. And then when we do the experiment for, again, silicate glasses and borate glasses, we see the same deviations we were observing for sodium species. So what we can say, in general, at least for these light network modifiers, is that for alkali silicate glasses, we tend to have clustering of the network modifiers, while that was not me. It's there. While for borate glasses, we have a statistical distribution of the network modifier species. Something else we can detect is the short range order in glasses. So we can look to each of these species here and infer how is the first order coordination environment of these species. Then to do this, usually we don't want all these interactions interfering with our signal. So we want to remove all of them. And all of them depends on the same angular dependence. That's this 3 cosine theta, cosine squared theta minus 1. Then why not spin the sample in an angle that makes this, this angular term go to 0. So if you spin fast enough, you can eliminate most of these interactions here. So as I'm showing here, the dipolar coupling goes out, the J coupling goes to isotropic interaction only. The chemical shift anisotropy goes out, then we have isotropic chemical shifts like in liquids, and this helps us to get more information. And for the quadpolar coupling, and I don't know if you remember, but we have 2 angular dependencies for the second order. So only the first order goes out, and we still have contributions from second order. So this is how our signal will look like when we are spinning the sample. So we introduce some periodic signal in our sample. And then what we usually do, we do the Fourier transformation of the whole FID. Then we get a pattern that sounds like this. So we have a main line here and what we call spinning sidebands showing up. If we make a Fourier transformation of the envelope, you would get an isotropic line like we have in liquids. And if you get only one of these fractions of the signal here, that's one of the spinning period, then you have an FID that will recover you the static line shape. So, but of course we need to spin fast enough. Then this is an effect of the spinning frequency in the spectrum. So for low spinning, we still don't resolve very well the isotropic shifts here. Then when we go to fast spinning, then we start seeing a main line here and the spinning sidebands that goes smaller and smaller with spinning rate. So this is an example. With silicon NMR, we can usually detect very well different silicate species. We can go from Q0 to Q4. We see very well resolved, sometimes, lines that can tell us which silicon groups we have in our samples, in our sample. But for quadpolar nuclei, we have this problem. That this is the angular dependence dashed line here of the first order perturbation term, the P2, the Legendre polynomial. And this is the dependence of the P4, that's where we have the dependence for the second order quadpolar interaction. So you can average out the first one, but you cannot average out the second one at the same time. So you need to pick up one to eliminate. We usually eliminate the P2 because we can eliminate more terms from that Hamiltonian. But we still have, for example, for the gallium phosphate, this is the static line shape. It's complicated. When you go to MAS, it gets more nice. It gets nicer, but we still have some structure in this line, and it can sometimes hinder determination, or it can sometimes help us to identify species. For example, for borates, we have a very nice environment for boron 3, and it has a planar geometry, so it has anisotropy, and this anisotropy is translated into this powder pattern here. So this is characteristic for boron 3. While for boron 4, we have an isotropic environment, then we don't have this distribution of frequencies like in a powder pattern. Then we have sharp lines here, and we can get, just by looking to the spectrum, we can know which one is boron 3, which one is boron 4, and so on. For boron 4, we can also get information from that spinning sidebands that I was speaking about. These spinning sidebands, they mimic the line shape we would have in the static spectrum. Michael. From this distribution of line shapes, we can also get information about the quadpolar coupling, and then we can resolve different species, even when it's not possible from the central transition line. Now I want to show the central transition here. I think I stepped somewhere. Ah. Then if you look to the, so here it's a low field spectrum. We have bottom 3 lying down here, and we have 2 bottom 4 species. And we couldn't resolve these 2 species if we didn't look to the spin side bands. So we can see this is the experimental data, this is a simulation, and the simulation is done by assuming 2 different environments for our system. This is the case where bottom gives nice information, not like the previous slide. So here you can see how the bottom 3 to bottom 4 concentration changes. When you change, for example, in a zinc phosphate glass, the concentration of zinc oxide, so you are decreasing the amount of phosphorus in the sample. So this line, the bottom 4 is shifting because we are changing the coordination with phosphorus, and we are creating more bottom 3 species. This is an example of another spin 1/2, the phosphorus. So it's a nice nucleus to measure in NMR. Here you can also detect the different species that we can have in phosphorus. So P1, P2, and P3, for example, where these numbers here means the number of oxygens that are sharing 2 network formers in the structure. So you can resolve these species very well in phosphorus NMR. Of course, we always show the nice examples. Now, this is an example where, in this region here, it's already hard to resolve phosphorus units. This is the same sample I showed before. It's a zinc bottom phosphate. So it has a complex line shape here because we have contributions from phosphorus-phosphorus interactions and phosphorus-boron interactions. So what we do in this case is we know that from the chemical shift tendency here, that we are going from a more coordinated network to a less polymerized network, but we cannot, from this spectrum, quantify what's happening. So another type of experiment that we can use to filter our information are selective experiments that detect only one type of interaction. For example, in this case here, if I have 2 phosphorus interaction with each other, then again I have a 4 states system. Then this first one is the first phosphorus, this one is the second, so we have all these energy levels here. And by appropriate pulse sequences, the pulse sequence shown here, we can excite this double quantum transition here. Although we cannot detect it, we can excite. We can let our system evolve under the influence of this double quantum coherence here, and then convert it back to the coherences we can detect and measure our signal. So if we can create this double quantum coherence, double quantum means we have 2 phosphorus with spins pointing up, and then I flip both of them together consistently. You need to have an interaction between them, so this happens in a sum system. Then if you can create this double quantum, means that you have phosphorus-phosphorus interaction, and you have a signal here. If you cannot create this, means that the phosphorus are far apart, and then you don't have a signal. And then you can filter your phosphorus spectrum, for example. Then you can look for the spectrum only with POP linkages, compare it with the spectrum where all phosphorus are contributing to the line shape, and then you can get more information about the components of these complex line shapes. So we can also investigate the medium range order, meaning that now we are going to the second coordination sphere. We want to know how one network former is coordinating with the other network former, for example. So to do this, again, we need an experiment that is based on the heteronuclear dipolar coupling. We could do this in static conditions like I did for lithium-6, lithium-7. Problem is that we usually don't have a single species in our sample. We have multiple species. So we want to spin the sample to have resolution of chemical shifts. But when we spin the sample, the dipolar coupling depends also on the same parameter. Then you are averaging out the dipolar coupling. So if you look here for one rotation cycle, one rotor cycle, the dipolar coupling goes up and down, and then in the end you have 0 again. Then the net dipolar coupling here is 0. But we want this to influence our spectrum so we can measure it. Then we reintroduce it with a pi pulse right in the middle of the rotor period here. Then when we apply this pi pulse here, you invert the contribution of this. If I'm observing the phosphorus species, for example, I'll invert the contribution from boron species, but the phosphorus will remain the same. Then we have this inverted contribution. Then the dipolar coupling, in average, is not 0 anymore, and we can then measure it. So it's done like this. We have a spin echo in one channel, and in the other channel, we will apply 1 pi pulse at every half rotor cycle. We do this over and over again. So when we go through the whole echo evolution here, we lose coherence because we are reintroducing the heteronuclear dipolar coupling, and this signal will decay, giving us information. The problem is we have some of the information here. It will always decay with homonuclear dipolar couplings. Then what we do, we compare with the normal echo, and then we take the difference. From the difference, we can get information solely on the heteronuclear dipolar coupling. So from this, we can get the strength of this interaction. That depends on the number of neighbors that we have and also on the distances. So if we fix the distance, for example, we can get information about the coordination. And this decay here will go through the dipolar evolution time. So if we measure it over time, then we have a curve that goes like this. So we take the difference against the main signal, that's the echo signal. So a high intensity here means a large difference. So when we have a high build-up here, it means that we have a strong dipolar coupling interaction. And we can measure the intensity of this interaction by plotting a parabola in the beginning of the curve here. This parabola you have as an argument here, again, the second moment that gives average information about the dipolar coupling in our system that we can correlate with structure from this equation that I've shown 2 times already. And here it's an experimental data, for example, for the BPO4 crystalline compound. So if you measure the dipolar coupling, we get this value here, 15.8. While the theoretical one, taking the crystal file, measuring all the distances, putting in that equation, then we have this value here. So usually what we do, we use a map, you see that we have an underestimation. Usually we take a model compound, calibrate our experiment, and then run the glass using this calibration factor. So here's an example, for example, for boron observed experiment, posting on the phosphorus. Then we can see how boron 3 and boron 4 are coordinating with phosphorus. So we see here that we have a stronger dephasing for BO4, meaning that BO4 is preferentially connecting to phosphate species. And from double resonance experiments like this one, boron phosphorus, if I take the opposite also, boron phosphorus, and so on and so forth, we can quantify the number of POP, BOB linkages in a boron phosphate system, for example, and compare the evolution of these units with statistical scenarios. So if it's completely random distribution of POP, and BOB linkages, we would have the solid curves here, and the experimental data gives us the circles here. You see that we have a deviation from statistics here. And then if we assume a scenario where we maximize the number of BOP linkages, we have this scenario here. You see it's much closer to the experimental one. Then we can say that in these borophosphate systems, the POB linkage is preferential. It's not a statistical distribution of heterolinkages. This is an example for aluminum. So aluminum is a nice quadrupolar nucleus because we can have information about coordination numbers. It's the chemical shift is sensitive to the species that are connected to aluminum. But you see that we always have not a Gaussian line shape. We have these tails here that comes from the distribution of quadrupolar coupling interactions that I have spoken about before. So sometimes these line shapes, they make things hard to determine. So it's hard here to say what's the line shape of each of these aluminum species here. We could fit different line shapes here. Then we have 2D experiments that can help us, where we correlate isotropic chemical shifts with the mass spectrum. So you open up in 2 dimensions, then you can resolve better your species. So this is an example, for example, for oxygen 17 NMR, where we can resolve oxygens connecting silicon, silicon with boron, and boron with boron, with these 2D experiments. So I'm concluding already. So I'll just show in the last slide some fancier techniques. For some nuclei, we have so strong anisotropic interactions that our spectrum can take a line width that's broader than we could measure in one single experiment. In these cases, we can use special pulses. By modulating the phase of the pulse, you create a variation in frequency. So you have a pulse that sweeps the frequency. Then you can measure a broader region than you would do with a simpler pulse. And this can be combined with what we call CPMD acquisition, where instead of acquiring a single FID, we measure here an echo, and then we put it in a loop, because you saw how the echo works, né? You have dephasing, we refocus, it dephases again, you refocus again. So if you put in a loop, you have multiple echoes here, and when you do the Fourier transformation, you can get information of our line shape with a better signal to noise. So this is an example for magnesium NMR, for example. These are enriched samples where you can see the mass line shape, and you can also measure the static line shape with these special techniques. For magnesium, the abundance is too low. You would need always isotopic enrichment to do measurements. But I will show in the end some techniques that we can also use to enhance the signal of some quadrupolar nuclei. So this is an example for tellurium. Tellurium has a strong chemical shift anisotropy, so we also need these Wurst pulses to measure the line shapes. And by correlating this, for example, this telluride phosphate glasses, correlating with phosphorus experiments and other experiments, we can find out also a distribution of the phosphate units we have in the glass, and correlate it with the properties of the glass. So this is the last example for magnesium, for example. It has a low abundance of 10.13%. It has a low frequency, which makes things difficult when we are doing the experiment. But we can have a nice technique to enhance the intensity of the signals. In this example here, enhance the signal up to 7 times. So we have here these Boltzmann distributions for magnesium. It's a spin 5/2. If you look to the central transition, that's this one here, the only thing that's giving us signal is the difference in population. Eh? So our signal is proportional to 3 here. So what we do, we apply a second pulse with an offset from this central transition to irradiate in a satellite transition selectively. So what happens when we saturate the transition is that we have equal populations for both states, and we have this scenario here, and the intensity of the signal will be proportional to 5 in this example here. So this is the last slide. I just wanted to connect my talk with Helmut's talk. So this is how we can put NMR and EPI together to get information about some system. So we have a system where we had Ytterbium C+, it's a luminescent species. We would like to know the coordination environment of Ytterbium in the glass. And we can do this by EPR. So you see here, this is the exam technique that Helmut showed. Each peak here corresponds to a nucleus that's close to the Ytterbium. If the peak is strong, the interaction is strong. If it's weak, the interaction is weak. So you see the fluorine peak here is very small. And then when we go to another system with indium, we have a strong fluorine peak and a small phosphorus peak in the other side here. And then we can compare with experiments done on scandium and phosphorus. Scandium is a mimic to Ytterbium. It has a similar chemistry. And then we can quantify the number of phosphorus to fluorine around scandium, for example, we have. We cannot do this with EPR techniques. So when you look to the scandium phosphorus redoor in the example, This first one here, we see an evolution with composition. It means that phosphorus and fluorine are going together with ytterbium statistically. And here, you see no evolution when we add more fluorine to the sample, more phosphorus to the sample, sorry. Meaning that the interaction of phosphorus with fluorine, scandium with phosphorus is small, is always small. And then scandium is preferentially connecting to fluorine species, as the EPR was already suggesting. So just as final remarks, so the first NMR is element selective. We have spin interactions perturbing our energy levels, and from this comes our information. You saw that we have multiple techniques that we can use to pick up one interaction at a time, so we don't have all the information together. That would be hard to analyze. Then we can select appropriate techniques to detect only the part of the Hamiltonian that we are interested on. And then we can get information about our system. So what I would like to thank you. That's it.
So thank you, Professor Marcos. We have time for a few questions. Come on, we want to hear some questions. Is anybody here in the audience doing NMR of your glasses? You are, no? For sure.
I have a detailed question about one of the redo curves you showed for result for the boron 3 and the boron 4. At the onset of the curves, you could see that there was a partial dephasing of the boron 3, and it was already below 0 at very low times. It was higher than what you observed for boron 4. I was wondering, is that like some kind of typical effect you often observe, or was it just in that one specific?
Here?
Yeah, there, close to 200 microseconds.
Okay, this is not my data, but probably we have the S0 signal also going down quickly because the quadrupolar coupling is more intense for boron 3. And then when you take the difference of something that's already small with something that's a bit smaller, it can have some deviations.
All right, yeah. Thanks.
Any other questions?
Thank you for the talk. I was wondering why we can't do indium NMR. As I saw in your periodic table, that was in impractical elements. We can do boron, aluminum, gallium, but not indium. What's the reason?
For this, I need to check the frequency of the indium. Let's go to the... let's see.
I think the other one that...
It's too down there. You start having strong electric field gradients, and then things get broadened beyond detectability. Yeah. For crystals, I have seen indium NMR, but for glasses, I think it's too broad to get information to Hamilton. Yeah, the quadrupole moment usually goes up when you go down the periodic table. Then you start having some of this broadening effect. The anisotropy is too big.
Other questions? Thank you for this meaningful presentation. I want to ask slide 10. You mentioned we calculate eigenvalues in here, and what do these eigenvalues represent in here? Why we calculate?
Yeah, if you think classically, they represent orientations of the spin quantum
And
number.
also we calculate eigenvectors or just eigenvalues we care about in here?
What? Sorry.
Eigenvectors or just eigenvalues?
Yeah, I have the eigenvectors also. That are the states. When I put these states there, these are the eigenvectors.
Okay. Thank you. And you mentioned you use simulation methods also. Do you calculate what is the accuracy of simulation methods and experimental So you calculate the accuracy of simulation methods?
Yeah, you're speaking about the radar calibration.
Yes.
Yeah, it's not simulation. We just take the crystal structure and calculate by hand or putting the software.
No, but it's
All the distance-
rate of accuracy.
All the pairs of different atoms we have, calculate all the distances, put in the equation that this one that's sum of 1 over r to 6, and then we get a value that's the second moment.
Thank you so much.
Okay, one more question. Yeah.
Thanks for the presentation. And I got curious about why homonuclear interaction, bipolar-dipolar, is not so important for glasses.
Yeah, the problem is that in glasses we have so strong distribution between environments that most of the times the homonuclear dipolar interaction behaves like the heteronuclear one, because the two neighbors, the chemical environment of them are different, and they are not the same anymore. Like they.
But sometimes you have to consider it.
No, sometimes yes.
Okay, so I understand you have a bus to catch to go to the cocktail, so let's thank our speaker again. And after the cocktail tonight, we will resume the sessions at 8 tomorrow, right, Laudi? Okay, so very important is to sign the presence. So there's a list there, you know, that shows that you were present here. So please do not leave without signing the list. And also picking up the money. Yeah, you also have to confirm if you are going to do the tour on Wednesday or not. So please talk to Laudi.